All right. So you had recorded lectures on Wednesday and Friday last week. Oops. And if you didn't get a chance to go through them, I definitely hope that you will before the exam, which we're going to have in class on Wednesday. And also Wednesday, homework 6 is due. And I think what I'm going to do on that is email you the answers to homework 6, just so that you know if you've got the right idea before you submit the assignment. Because you're submitting the assignment on the same day that we're having the exam. So if I give you the answers today, then that'll let you know if you've been on the right track for homework 6. You should bring your computer again to the classroom on Wednesday, because you will have some need to use Excel during the test. And I was looking back through Blackboard. I think I've given you 4 templates so far. There's the template for pipe sizing. There's a template for pipe sizing with a pump. There's a template for 3 reservoirs. And then there was one for the Hardy Cross. And you can't use any of those templates on the exam. You just have to start from a blank workbook and just off the dome and with the equation sheet, figure out how to solve the problems that are given to you. And so, I mean, I recognize you may not memorize every step of a problem. What I'm hoping is that you'd be able to think through the process and know the procedure well enough to solve it. And it doesn't have to look exactly like the way that I solve it. There's, multiple ways to organize an Excel solution for a problem. But we'll have that exam 48 hours from now. The equation sheet's on Blackboard, so if you want to get an early look at that and see how it's situated and where the formulas are and which equations I'm providing, then please feel free. So are there any schedule-related questions? Anybody want to ask anything before we jump into WaterGEMS? No? All right. Does everybody have a copy of this example file that I've given you? I printed it intentionally so that it would just take up half the page, thinking that you could use the lower half of the page to take some notes on the step-by-step. Kind of like bullet point 1, switch to SI units, that kind of thing. So let's take a look at this network that we're going to be solving. I think this is similar to a network we've seen before, right? We've seen this same network, and we solved it, I think, when we were doing the in-class example related to the Hardy Cross method. And so there is one slight difference to how it was presented in the previous example. In the previous example, I just said what the pressure at A was. Now, when we are going to be setting this up in WaterGEMS, the way that I make the pressure at A 600 kilopascals is I'm going to attach a reservoir with a very short pipe to junction A. And then I'll put enough water in the reservoir to pressurize junction A up to 600 kPa. So, I mean, it's just, it's the way that we make that true. And then the other difference is that I'm going to add a reservoir at D, because water is coming into the network at D, and the way that WaterGEMS thinks about things, there has to be somewhere the water's coming from. And so I have to provide a source of the water. And the source in this example is going to be a reservoir, and I'll define the elevation of the water at that location to be 57.83, because the water surface elevation has to be something, and that happens to be the water surface elevation that is consistent with the pressure that was observed in the previous example. So with those 2 additions, I think what we'll see at the end of this example is that the flow rates match up with that example we did previously when we were using the spreadsheet method. When it converged, it's going to give us the same flow rates and the same pressures that we'll calculate with WaterGEMS. By the way, there's 2 very similar products available from Bentley. One is called WaterCAD, and one is called WaterGEMS. And WaterCAD is a subset of WaterGEMS. WaterCAD has fewer features. We won't use any of the extra features in WaterGEMS. The only reason we use WaterGEMS and not WaterCAD is because, for whatever reason, Bentley will only allow you to have a limited number of junctions in WaterCAD's academic license, and it's not enough for the project that you're going to do. So we have to use WaterGEMS because it allows you to have more nodes in the network. So I just wanted to point that out. Okay, so what we're going to do is, first of all, you have to have connection client running in order to get the program to work. And so this is just an annoying little license activation tool that resides down here in the system tray. And I'm going to make sure that I'm logged in. See, IW, that's me. So I'm logged in. And with that connected, now I can just WaterGEMS is the one that I want. And it's going to feel familiar to you if you've used any kind of CAD program. You know, it's drawing lines. We're not using any of the integration for AutoCAD or MicroStation. We're just going to do the standalone version of WaterGEMS. It's simpler. We don't need the extra functionality of integrating. So create a new hydraulic model. So it's this one in the middle. Create new hydraulic model. It'll take a moment to initialize. If it's your first time using the program, it's probably going to default into British gravitational units. So what we'll have to do is switch it into SI and then restart the program. So go here to Tools. So we're on the Tools menu option. It brings up a option-specific ribbon, and then under More, select Options. Is this recording? Yeah. All right. Under More, select Options, and then Units. See how it says US customary? They're not even pinning it on the British anymore. I usually call it British gravitational, but I guess we're the only ones who use it anymore, so US customary. All right, so switch it to SI. OK. And now we have to restart the program. So exit. Don't need to save it. But when we restart in next time, it will remember that in the previous example we had SI. And the reason why you have to restart is even if you set SI units, about half the time it won't remember that. I don't know why. It just kind of is a little bit laggard in switching over the units. And so we start from scratch, and we're going to verify that this time it's in SI. So if we go to Tools, More, Options, Units, SI. Okay, so we're good there. So here on your handout, put switch options to SI and check.
Do you have to restart it for SI units?
No, it's not like you're going to have to restart every time.
It's just that way every time you get back on there, it'll have the SI units now.
Yeah, check if it's got the SI, and if it does, you're golden. If it's there from the beginning. So we don't have to restart another time. All right, so the next kind of preliminary thing before anything else is let's tell the program we want maximum accuracy, and that means Darcy-Weisbach. Because for whatever reason, I don't understand it, they have the model set to Hayes and Williams. We know that Darcy-Weisbach's more accurate, and I don't care if it takes the computer 9/10 of a second instead of 4/10 of a second to calculate the flow rates. So I'm going to go under Home, Options, Base Calculation Options under the Steady State Solver. So just double click on this first place where it says Base Calculation Options. And then see where it says Friction Method Hayes and Williams? Let's change that to Darcy-Weisbach for maximum accuracy. Okay, we close it, double check if it's there. Yep, Darcy-Weisbach. Okay, so the preliminaries are out of the way. We've got the SI units and the maximum accuracy friction method. So we can begin drawing. There's two ways to draw. One is to draw to scale, like if you have a map or a picture in the background. One is to draw conceptually and then to manually define lengths. For today's example, we're going to draw conceptually. For the project, I'm going to give you an image that you can bring into the background, and you're going to draw on top of the image so that your pipes are automatically the right length. For today, we're just going to draw conceptually. And so this is what I want to draw. I want to make an approximation of this in WaterGEMS. And it doesn't matter like how long the pipe is that I'm representing as AB, because I'm going to go in and manually tell it that pipe is 220 meters. So here I'm going to draw pipe AB, and it's this layout tab that we're going to start with. So you can see the little circle cursor, that's a junction. So I'm going to click, that's pipe junction A. Right now it's calling it J1. I'll go in and rename it later. Here is B, C, D, F, E. I'm going to connect back to this one, which is junction C, and I got to click right on it because I don't want to draw another junction. I want to snap to the existing one that's there. Okay, now I need to press escape to cancel this next pipe that it's drawing, because my last step is to connect what it's calling J1 and J5, which I know as A and F. So escape, and then connect the two by just clicking on J5 and J1. All right. So it doesn't matter that those lines aren't perfectly vertical and whatnot, because the orientation of the pipe, this is a top view, the orientation of the pipe doesn't change the hydraulics. It's just a matter of the length, the flow rate, the friction type, and so on. Okay, now I want to put in those two reservoirs. So if you right-click on your mouse, right-click, see this is the list of options, and right now we're on junction. Switch to reservoir. So you right-click to get that menu up, and then left-click on reservoir, and then just drop a reservoir close to J1. Okay, so that's calling it reservoir 1. Now look, my cursor is a reservoir, so I need to switch it back to junction again. Junction, and then tie it into J1. So let me show that same process again over here at D, at what it's calling J4. So right-click to get the reservoir, drop a reservoir in the proximity of junction D, and then right-click again to get it back to junction, and connect the dots. Okay, so now I have a model. I've got the schematic of our system. I haven't yet told it the diameters or lengths. I haven't yet told it the elevation of the junctions or the elevation of the water. All of those things I'm going to define. So any questions so far? Does anybody need to see a certain thing? Of course, remember, this is being recorded. So if you fall behind or your computer crashes or does Windows update, go back through the video. And in fact, it may be a good idea just to reinforce this, to work through it again this evening. All right, so I've got a system. Let me rename the junctions because I want it to be looking the same as this one. So there's a couple ways I can do that. One, let me click over here on the select tool. See this ribbon at the top? So click on the select tool and double click on J1. So if I double click on J1, it brings up a whole pile of characteristics about it. Look at all these characteristics. All of that applies to J1. But here at the top, instead of calling it J1, I'm just going to call it A. And when I close that, it updates the label, this annotation for the junction, A. And over here I could do that for B. This is tedious, opening them up one at a time. So a better way to do it is to open the flex tables. And so here on the home menu, home, and then the ribbon across the top, one of the options is flex tables. And click on the little arrow that's beneath flex tables, and we're going to open up the junction flex table. So when the junction flex table is visible, what we can do now is just go through one at a time without having to open a menu for each one of them to relabel those. So J3, that's C. J4, that's D. J5, that's F. And J6 is E. All right. Now look what else it's knowing about these locations. It says elevation, zone. You're not going to do anything about zone, but elevation is talking about what's the physical elevation of that junction. For our example that we're working here, we assume that all of these are at the same elevation, and let's just say that's the elevation datum of 0. In your project, I'm going to give you a map of a city, and it's got elevation contour lines. And so you're going to have to actually put the physical elevation of the ground, or maybe like ground minus 1 meter. It doesn't matter, but you're going to have a different elevation for every point in the network for the project. For this example, we'll leave it at 0. All right, so let's close this. We've renamed it. I don't necessarily need to see the pipe names, P1, P2, and so on. So let me point you towards over to the left here. These are the annotations, and see where it says pipe. Right now the pipe name annotation is selected. So if I turn that off, it's got a checkbox now, but if I turn it off, oh no, those are the pipes. We need those. Label, it's the label. So expand it, and turn off the label. Because I'll just call it pipe AB. You know, I'll name the pipe by its origin and destination junction. So you can turn off the annotations using these menus. All right. On the subject of annotation, let's add some annotations like the diameter of the pipe and the flow rate that's going through it. Okay, so you know how I just turned off the labels? We can add more annotations. Right-click on the word pipe. So right-click on the word pipe and then do New Annotation. And here in the drop-down box where it says Field Name, drop down to Diameter. Okay. And rather than just have the numerical diameter, like if you clicked Apply, it just shows the diameter and it's on top of the pipe. We'll fix that. I think it's better if we have a label. So I'm going to have here under prefix, I'm going to have D space equals space, and now apply. And now it says D equals 152.4 millimeters. So that's a little bit better. Now to get it up off of the line, I'm going to do an offset, a Y offset. So see where it says initial offset? We can manually drag each one of these annotations one at a time. But if we just want all of them to be up off the line a little bit, let me do a 2-meter offset. So I've just put 2 into the Y offset and then apply. And now they're not on top of the line. And so that looks a little bit better. You'll notice down here there's a height multiplier. What if for some reason the labels are really small? Usually that happens when I've zoomed out a lot and I've started drawing my network zoomed out. Now the labels are small. You can change the size of the annotations with this height multiplier. You can make them bigger or smaller, however you like. In this case, a multiplier of 1 looks good to me. Okay. So we've annotated the diameter. Okay, let's do another annotation. Let's do flow rate. So right-click on the word pipe, New Annotation, and under Freeform, scroll down to Flow. Look at all those flow options we've got. There's Flow, Flow Absolute, Initial, Maximum Absolute. There's 2 types of analysis that you can do in WaterGEMS. You can do an analysis with transient flow rates. So you can tell it, I want to look at how the system is going to behave in the middle of the night, in the middle of the day, at 2 o'clock, at 1 o'clock. You can define a range of flow rates. That's pretty hard to set up. That's beyond the 30 minutes a year that I use the program. Let's just do a steady state analysis where what we're going to put into the system is our maximum expected flow rates. So that if the network performs okay at the worst case scenario, then we know everything's going to be fine under other conditions as well. So the flow rate I want to do is flow absolute. And the reason why I want flow absolute instead of flow is you remember how clockwise is positive, counterclockwise is negative from the Hardy-Cross method that we did on Excel? It will give you negative flow rates if the water direction is counterclockwise. And that's just, it looks weird if you have negative flow rates. So we'll just annotate flow absolute. And then here under the prefix, I'll do Q space equals space. And then the Y offset, I'll do -2 so that it's below the line. Now there aren't going to be any flows yet, so when I apply, it's going to say not applicable liters per second because I haven't defined any flow rates yet. But we're getting the annotation set up for when we do put in the flow rates and calculate. Everything will, all the answers we need are on the screen. All right? Any questions? Okay, so let's click on OK. And let's also annotate the pressure at the junction, because if we go back to the example, what is it asking? Flow rate in each pipe, pressure at each node. All right, so let me now right-click on the word junction, because we're going to add a junction annotation, which is the pressure. So right-click, new, annotation, and so scroll down on the field name, and we want pressure. And then for prefix, I'll just have P space equals space. And then I'm going to need an offset. And this is hard to predict in advance. Let's see what -1, -1 looks like. It's probably going to be in the way. Apply. Yeah, it's definitely in the way. Let's do -3, -3. That seems all right. I maybe will go back and change some of them, drag them out of the way. For example, here at D, it's a little bit crowded, right? So let me click OK, and then here at D, I can drag that one down a little bit. So that's not quite in the way like it was, and maybe this one I could move over. All right. So we've annotated. Now we need to put in the pipe details, because let's take pipe AB. So double click on pipe AB to bring up its properties. Right now, how long does it think that pipe is? It thinks that that pipe is 55 meters. So it thinks the length is 55 meters. Why does it think that? It's just based on where I clicked on the screen. How long is that pipe supposed to be in our example? 220. So there's a way for me to tell it it's a user-defined length. Don't use just where I clicked, but let me type that in manually. So go here to the flex table for the pipes. So in the pipe flex table, scroll to the side, and one of the options is has user-defined length. And let's click the checkbox for each of those. And look, when you click the box, it's turning this last one from yellow to white. Yellow means it's a calculated field or non-editable, but if it's white, that means you can directly put data in. So when I'm clicking this, it's making it so that I can put in the lengths that they're supposed to be. So for example, this first pipe, I guess I probably need to rename the pipes. Here under the labels, let's call the pipes just based on their start and stop nodes. So P1 is AB. P2, BC, and so on, right? And then these ones that connect the reservoir, I'll just leave those as the names that they are. Okay, so here's the diameter, and over here is the length. Let me make it so that those two columns are closer together. Let me drag it to the side. See, if you click with the left mouse cursor and drag it over, you can move where things appear. So right now the length, I want to move the length next to the diameter so that I have an easier time changing both of them. All right, so you've got the handout, the printed handout. So let's look at AB. So AB should be 220 meters and 500 millimeters in diameter. So let me put the length first and then the diameter, because that's how it's annotated on the handout that I've given you. So the user-defined length for AB is 220, and then the diameter is 500. Okay, BC, 100 and 650. CD, 80 and 850. DF 200, 500. EF 80 and 700. CE 150. Oops. 150 is the length, and the diameter is 600. AF, the length is 180, the diameter is 400. All right. For these other pipes, like I want it to have as little head loss as possible through these pipes that connect it to the reservoir. I mean, for this example. In your project, it's a different story, but the purpose of the reservoirs here is just to pressurize the junction. So let me make it relatively short. Let me say it's 10 meters long, and then I'm going to make it a really large diameter. I'm going to make it 1,000 millimeters in diameter. And the reason why I'm making it so big is just so that there won't be any head loss through that little pipe that connects the reservoir to the network in this example. See how it says Hazen-Williams C? Don't be worried that it says that. We set it to Darcy-Weisbach, and so it's going to base the roughness under the material here, ductile iron. And for our pipes, it is ductile iron because 0.3 millimeters is associated with ductile iron. But it has lots of fields that don't necessarily get used in the calculation. So the fact that it has a Hazen-Williams C, it shouldn't throw you off. Okay, so we've defined the diameter and the length of each pipe. There's only one last thing that we have to do before we can calculate, and we haven't told it anything about flow rates. And the way that WaterGEMS works is you don't tell it how much water is coming in. It figures that out on its own. But you do tell it where the water is coming out. And so look, on this network map, where is the water coming out? It's coming out at B and at E. And so we'll tell it where the water comes out, and then it will calculate how much water needs to come from each reservoir. All right, so let's go to B and E and tell it the flow rates that are needed. I like to do that through the flex tables for the junction. And the place that we're going to do it is, it's a strange field, I don't know why they call it that, demand collection. And even though it's yellow, we can edit. And so for B is one of them. So B, how many liters per second is coming out at B? 600 liters per second. Do you see where it says 0.6 cubic meters per second? That is 600 liters per second. So at B, I'm going to do a demand collection. Click on the little ellipsis that comes up. That is the ... button that appears onto the side. So demand base 600 liters per second. Okay, so we just defined it at B, and then the other one we want to do it is E. And so do a demand collection, click on the ellipsis at E, and it is 1,600 liters per second at that location. All right. So let me just make sure that it's got the one at B. Yeah, it's there. 600 and 1,600. Okay. We are set to calculate. Now, you'll notice it didn't tell us the pressures or the flow rates yet. It hasn't done any calculations. We have to click on a compute button for it to run the model and go through the process. In the background, it's doing what we set up in the spreadsheet. Same method. What it's doing is it's looking for balancing continuity at each junction and making it so the head loss is the same regardless of which route you take between junctions. So here we have an indeterminate system where the water could be coming from A towards E, either through this upper section or through this lower section. It'll go through the same process that we did once I click on compute. So let's do that. And it should only take a moment once we click it. It's pretty quick. And this is the result. Green is good. If you had like pipe diameters that were too small so that all of a sudden it's calculating like negative pressure at junctions, you may get a little error message or like a red icon or a yellow icon if there are warnings or if there's like a critical warning. This summary will give you an idea if something's wrong. Like if the pipe diameters were too small and the water actually couldn't flow as needed, then it would give you an error message, and then that would just tell you I need to make the pipes bigger than they were before. But let's just see what the flow rates are. So it's told us the pressure at junctions. Oh, there's something I didn't do. I didn't define the water surface elevation at the reservoirs. I'm surprised it didn't get, well, we do have negative pressures. See that? Look at junction E. The pressure is negative 24 kilopascals. And the pressure at A, it's saying is 0 kilopascals. And so the example, it's supposed to be 600 at A. So I need to define the water elevation in the reservoir. I forgot. Let's do it now. So go into the flex table for the reservoir, and reservoir 1 is the reservoir where the elevation of the water should be 61.162. Reservoir 2 is the reservoir where the water surface elevation should be 57.83. All right, now with that, I'm surprised it didn't give us the error because obviously we don't want negative pressures. We'll compute again. And just that easily, now we've got updated pressures and flow rates. Pretty good, right? Pretty good. Let me see. I don't know if I have the solution to that example that we worked before. I'm not sure whether I've got it handy just to compare. That was the Hardy Cross. Oh, I think I've just got the blank student start at the ready. Well, we need to save the time anyway to talk about the project. But, all right, now let me show you the real power of this program. For you, what you're doing is not just analysis. This is analysis. We're taking the given diameters, the given lengths, and we're saying what the pressure is. That's analysis. The next step, which is a step above analysis, is design and optimization. What if the rule was you could only, well, your pressure can go as low as 240 kilopascals. What if that was the allowable minimum? We've made the pipes bigger than they need to be. If the allowable minimum is 240, we're leaving money on the table. We're wasting money because we bought pipes that were too big. So let's try and optimize this network. For example, what happens everywhere in the network if we just change pipe AB? Like right now, pipe AB is 500 millimeters. What if I bought a cheaper pipe? What if I bought the 400 millimeter pipe? Okay, so now look. Right now, the pressure at B is 564. When I change that to 400 millimeters, it doesn't change it yet. I have to compute again, but I've changed the diameter of pipe AB, and it's going to go from 564 down to 562. We only lost 2 kilopascals at junction B, and we saved the client a lot of money by going from a 500 millimeter pipe to a 400 millimeter pipe. So optimization is make a tweak here, make a tweak there, keep lowering the pipe sizes until you're barely meeting the required minimum. And you know, the required minimum is what's allowable, and you only barely have to meet it. So what's the biggest pipe in this network? Besides these reservoir connecting ones, it's this pipe that's 850. So where is that? What pipe is 850? Okay, it's CD. Pipe CD is wildly oversized. What happens? Am I above the minimum if I change it from 850 down to 300? And I'll calculate again. Yeah, I'm going to get away with it, no problem. Everywhere is still above the minimum of 240. So I just saved tens of thousands of dollars with that one optimization. So that's what you're going to be doing in the project when you get to phase 2. In phase 2, you're going to break out WaterGEMS and begin drawing your network and optimizing it. Okay, so before we talk about the project, are there any questions in how you've used the program WaterGEMS today? I would love it if you stop by my office and, if you've got questions, we can go through it together. Of course, the video's online, so you need to be this proficient at WaterGEMS to do the project. You don't need anything beyond what I've just demonstrated for the project. So let's talk about the project then. Let me bring this up on screen and give you a couple of handouts here. By the way, you should put WaterGEMS on your resume after phase 2 of the project. You should list it as a software package that you're familiar with. Because you'll know it well enough to, hit the ground running if you go to a firm where they use it. You won't be as good as the guys who do the design on it, but you'll be able to open a design. All right, so here's your city. And on the last page of the handout I've just given you, you'll find your name, and you'll see where you're assigned. Some people have St. Louis, someone's got Miami, someone's got Seattle, and so on. Your design project is to estimate how much water they're going to need at different parts of the city and design the main pipelines, not every little lateral and connecting pipe, just the main pipelines to connect from a reservoir, which is up here around the 300 elevation. This is a contour map. These little brown lines are elevation contours. I'm going to give you a printed copy of this. I meant to bring it today, but I'll bring it for you on Wednesday. I'll bring you an 11 by 17 version of this map that's printed to scale so that 1 centimeter on the map equals 100 meters in this hypothetical town. So let's just say this is a land development exercise where you've got some town that's on a hillside, and what you're doing is you're taking water from a natural spring up at the top of the hill and you're piping it towards the network at junction A, and then water is going to be going into the network at these green arrows. For example, in the north zone of this city, there's both residential and commercial demands. And all of those interior residential and commercial demands are satisfied by these 2 green arrows, by the flow into the network at A and into the city at M. All of the water that's going to the sports stadium exits the network at B. The east zone, which I think has like a box factory, here's the box factory. I think the east zone has a hotel and a food processing plant, a few other things. It gets its water split evenly between C and E. You'll see there's a housing project, a hospital. So phase 1 of the project, what you're going to be doing is you're going to be saying, based on the population density that I'm assigned, that detail is on here, you've got an assigned population density. From the scaled map that I provide, you'll be able to calculate what's the area of the north zone. So maybe it's 50 hectares, and you've got 100 people per hectare. So now that tells you how many people are in the north zone. And then there are some materials that I can show you that's posted on Blackboard that says, like on a nationwide average, the one person uses 220 liters per day. Of course, what you should do is not use that cruddy data I'm providing. A nationwide average is useless if you're designing in Houston. You want to know what's the per capita water usage in Houston. So you'll do a Google search, you'll look online, maybe go to the City of Houston's website or Houston Municipal Water District or Department of Agriculture maybe has a report on Houston. Somebody out there has better data than I'm going to give you. If you use the cruddy data that I've provided, that's okay, but that's not like top-notch effort. You'll pass the class, you'll get an okay grade on the project if you use the supply-demand estimation data, which is nationwide averages. But the A students who really excel in this project are going to go get better data than I provide. That's the expectation. That's what we've done in past years. So you'll find out how many liters per person per day. You'll know how many people are there. And so you'll say how many liters per day are they using in the north zone. You'll do an analysis to figure out how much water do they need at the football stadium. That's not going to be necessarily based on liters per day. You may wonder, well, we'll talk about the sports stadium in a minute, but the point is you have to figure out how much water is coming out of the network at each of those green arrows. Just like we did in this example. What do you tell WaterGEMS? You tell it where the water is coming out. And then how big should the pipe be is depending on the allowable pressures and the flow demands. So you'll be doing that same process in this project. You'll be answering how much water is needed at each of the locations where there's a green arrow, how big should the pipes be, and what location should the pipes be. By the way, this black line is not the pipe. This black line is the city limits. So what's the most efficient route to get water from K to I? So here's the city limits. What's the most efficient way to get water from K to I? A straight line, right? So you wouldn't want the pipe to go along here and then there because that's just, it's too long. So part of what you're doing is optimizing the size of the pipes, and part of what you're doing is optimizing the location of the pipes. So for example, is it better to have water going from A to L and then to M? Or is it better to have the water go from A to L and from A to M and from A to B? Like, what's going to minimize the overall length of pipe? So it's an optimization exercise in that regard as well. You'll also be sizing a reservoir. We'll talk more about the reservoir in a future class. That's the third phase of the project. There are draft submissions, and your first draft submission of the flow demand estimates is due on Monday, March 4th. That's on the front page of the handout here. Monday, March 4th. By the way, this handout that I've given you, you really, really need to read it, every word. This is like the product of, I've been doing this project for about 18 years, and every year based on the mistakes that students make, I try and clarify the language a little bit further. And so there's a lot of important details in here, and you need to read it word for word, maybe more than once. So here's an example of the demand estimation data that I've given you on that last page. I'm telling you how much water is needed for fire, how much water is, how many guests are at the hotel, how much water they need at the food processing plant, the number of stores in the mall, number of seats in the football stadium, and so on. How do you think they use water at the football stadium? Like, what are some of the ways that water gets used at a football stadium? Bathrooms. They water the grass. Of the two, what do you think has a bigger flow demand? Watering 100 yards by, what's the width of a football field, like 40? It's a little bit of grass. Or like 35,000 people using the toilets all at halftime. It's that. It's the toilet use, and maybe they're also, I don't know, the water fountain or washing down vomit or whatever, you know. So you need to figure out how are they using water at all of these different places, and so read the handout and that'll help you. One of the things is the average daily use, 220 liters per person per day. You don't use water at a constant rate through the whole day. There are certain times of the day where you use a lot of water and certain times of the day where you're not using any. And on a population basis where you get tens of thousands of people together, some people are night owls, some people work during the day, and on average, this is what the temporal distribution of water use looks like. You know, on the maximum day where it's really hot and maybe they're irrigating the yard, if it's a dry climate, and people are washing their dishes and so on, the peak flow is typically in the evening. And the factor that you should use is the worst case scenario for designing your network. You know, like what's the worst case scenario in the residential area? It's either going to be the maximum daily flow rate plus fire demands, or the maximum hourly flow rate. And so the peaking factors are 1.8 to find the maximum daily flow rate from the average daily flow rate, and 3.25 is the peaking rate. You multiply the average daily flow rate in liters per second by 3.25, and that tells you the maximum hourly demand for a residential area. Not all flows are peaked, though, and this demand forecasting summary table is what you're going to submit on Monday, March 6th. You're going to submit this, a bunch of supporting hand calculations, and a brief write-up, like a typed summary of what are your data sources, what are your assumptions, what was your thought process, so that I understand how you came up with the demand estimation for your city. Now, the structure of this summary table has also evolved over the years to reflect what data you need to provide. So residential demand, you'll notice it's got the average daily flow rate, the peak day, peak hour, peak day plus fire, and then the design flow would be the largest of the peak hour or peak day plus fire, plus the commercial peak hour. You'll notice that intentionally, there's no cell here. It's because commercial demands aren't peaked for fire flows. They have sprinklers in commercial buildings, and so we don't have to add extra flow capacity in the pipe above and beyond in the same way that we do for residential structures. So just be aware that the structure of this summary table is intentional. I've got a copy of that for you. Maybe grab it on your way out because we're running really low on time. I've got one more minute before we run out of time. That summary table is also in Blackboard. Here are a few hints. This is definitely worth the 1 minute. They don't water the grass 24/7 at a golf course. Seems obvious, right? Why wouldn't they water the grass 24/7? Because people are out there golfing, and they're not spraying the golfers as they're golfing. Why does this matter? Because you have to determine how big should the pipe be to the golf course. So the grass needs a certain amount of water, and you're not going to consume that water over 24/7. You're going to consume that water over a fewer number of hours per week than all the time. Okay? Football fans are in the stadium about 4 hours on game day. They're not there for 24 hours. And so you'll calculate how much water do they use at the football stadium during a football game. You'll think, well, the average person's going to go to the toilet twice, and then I also want to give some water for something else. You'll figure out how much water they use at the stadium. Don't divide that water use over 24 hours because it's not. It's used over a concentrated period. Same thing about a food processing plant. Think about how much is it going to be open. Something that's like just a factory. Maybe it's open 24/7 and they're using a certain amount of water over a big number of hours per week. But conservative means be careful. What if they're only open 40 hours a week and they're using a certain amount of water over less hours? Then that makes the flow rate higher because Q is volume divided by time. And so if time is fewer hours, then the flow rate is going to be larger. High density housing is similar to dorms. And then the number of people at a hospital is the people who are staying in the rooms that are there, people who are coming in and out during the day, and then also the employees. Okay, so those are just a few hints. That's all I've got for you today. We'll talk more about the project. We'll talk more about WaterGEMS. For now, you should be thinking exam. We've got an exam on Wednesday, so I'll see you then.